All right. Hi, everyone. Everyone settled? Cool. All right. My name's Amy. I'm a CSE major here at UCI. All right. I'm a CSE major, so today we're going to just be talking about how to get started in AI. I'm going to be providing you with like resources because there's a whole lot of information out there. So, yeah. So what we're going to be doing today is we're going to be like discussing some notable people and resources in AI. Jason's going to be going over Jupyter Notebooks, Collab, and the Google Cloud. And then Monish will be doing an introduction to reading machine learning research papers. Yeah, so that's what we'll be doing today. So, also, our next workshop is also going to be next week. Still debating on the time. I think it's going to stick to 6 to 7. It might change to 5 to 6. So I'm not entirely sure about that yet. But we're having a discussion panel on AI in academia versus AI in the industry. So we're going to be having Professor Eiler and Professor Singh from here at UCI being on the academia side. And then we're also going to be having Dave Newman from Google for AI in industry. He worked at Google AI Research. And then we're still waiting on one more person. So yeah, it'll be a really good panel. It's going to be like a Q&A session, so any questions you guys have, you guys are welcome to ask them whatever you're curious about. So, some notable researchers in AI. So there's Fei Lei over here. She's a Stanford professor. She has some online courses that are really good. She's also a co-founder of ImageNet. This is also Demis Hassabis. He's the co-founder of Google DeepMind. And the main thing of Google DeepMind is they built an AI for AlphaGo, or called AlphaGo, for the game Go, and it actually beat the world's best Go player. Then we have Andrew New. He's a co-founder of Coursera and Google Brain, and if you guys aren't familiar with Coursera, it's basically a website that provides like a ton of courses on any AI-related topics, and actually Neil took the deep learning course, if I remember correctly.
Yeah. So I've taken some of Andrew's courses that are part of the deep learning specialization on Coursera, and I just wanted to share some quick thoughts that I have with you guys. So basically, the course is structured as a bottom-up approach to teaching neural networks, which are powerful nonlinear learning algorithms. And it's also designed as basically good curriculum and good instructional videos. And like the first course basically introduces you to core ideas for building neural networks, such as loss functions, gradient descent, and parallel Python computing. Overall, I think Andrew Ng basically explains the math and programming concepts in a well-paced form that is suitable for beginner learners. So if you just want to learn about neural networks, I would recommend watching some of the videos at least.
So some free online video courses that are available that I personally liked were the machine learning course that Neil mentioned, Neural Networks for Machine Learning by Jeffrey Hinton. These are all on Coursera. Udacity is also a really good resource. So they have all their videos for free, but like if you want like the official like nano degree, I think that costs money. I don't know how much it costs, but the videos are a really good resource. Then there's also a practical machine learning tutorial with Python, and that's a YouTube channel called CentDex, and he's really good. So yeah, so some YouTube channels are CentDex, 2-minute papers. They're kind of like just little short 2-3 minute videos, more science papers, but also quite a few AI videos. 3 Blue, 1 Brown. He got me through like half my math courses, so he has really good explanations for a lot of things. Some free books that are online that the PDFs are available for is Understanding Machine Learning from Theory to Algorithms. And then there's also Machine Learning Yearning, also by Andrew New. He's kind of really prominent in the field, so you'll see a bunch of resources from him. So yeah, we're going to get to coding, training, and deploying.
Hey guys, I don't know if some of you were here last week, but we did the Flappy Bird algorithm AI. I know some of you guys got some glazed over a little bit, so this is why we had this workshop this week. Kind of just like the baseline on how to do stuff, where to start if you don't know anything, and that's totally fine. We were all there at some point. We still feel like we're there all the time, but I'm going to show you kind of a good way, like progression, where to start to get up to like a solid level. And I have like a really cool workshop bootcamp for you guys, which you can download and work through yourselves. We won't do that today, but I'll show you where to get it. All right. So when you're training a model, and when we say model, it's like the machine that's going to be learning, right? That's when we call it that. We got 3 different ways you can go about it. So if it's something small, Jupyter notebooks are great. I'm going to show you exactly what they are. They're kind of like an IDE that you can use to train your models in, that works off your own computer, and it's pretty simple to train them and deploy stuff. If you need something bigger than that, like I know this weekend, Ryan and I were at SD Hacks, and we were building a model that on about 1,000 of our records, we had 19,000, and on 1,000 of them, it was at 12 gigabytes of memory. So Collab gives you like a really nice kind of Jupyter notebook style and runs on a GPU, which is a graphic processing unit, and gives you 12 gigs of memory, just free to use. And I'm going to show you how to set that up in a minute. And if you run out of space even on that, some models take like weeks, sometimes days to train. Google Cloud is awesome for that. It does take some setup, and I'll show you kind of where to go, but we'll probably, if you wanted to go into it a little bit further, I would definitely try to do like a workshop on Google Cloud, because it is pretty complicated and finicky to set it up. But I'm going to go through a few of these. All right, so Jupyter Notebooks, like I said, they run locally on your computer. So if you have Python 2 or Python 3 installed, you can just run Jupyter Notebook, and I'll show you that in a minute. It'll pop up like a really cool server, and you start coding. So what's cool about it is that if you guys taken like C, Java, Python, you have a program and you have to run the whole thing every time you want to run something, right? So you have your start, and it has to run all the way to the end to get your output. Jupyter Notebooks are cool because you can write code in a cell. So like you can run one piece of code and just keep running that a bunch of times. So you don't lose any variables, you don't have to restart the program, you can just run the one piece. And I'll show you that in a second. One thing it doesn't do is if you close the Jupyter Notebook, it deletes all your variables, so you have to rerun the whole thing. But it is like super, super quick to set up. And like if you want graphs to pop out and you can save it like that, it's super cool instead of having to write like a whole extra paper. So I'm going to show you how to do that, and then I'll come back to Collab in a minute. You don't have to run these commands right now, but the simplest commands to like get this set up, you just go pip install Jupyter, and if you want it for Python 3, you go pip 3. If you guys don't know what pip is, it's kind of awesome how they did this. Pip stands for pip installs packages. It's like the best name ever. But that's what you do for Python. So I'm going to show you, I'm going to exit out this presentation and show you just a second what Jupyter looks like and what the bootcamp I have for you guys that you can download later. All right. So you have to do it from your terminal. If everybody can see that, everybody's good. So so right now I'm in my desktop, like just on my desktop over here. I have the thing that you'll download is called Python Data Science and Machine Learning Bootcamp. So I'm just going to CD, so change directory into that, just like this. Cool. And all I have to do is go Jupyter. So once you've done those pip commands, go Jupyter and then Notebook. Just like that, hit enter, and it's gonna load it up and bring up this in your web browser. So this runs in your web browser. You don't need it to run on anything weird. Just runs right there, which is kind of awesome. So in this bootcamp for you guys, we've got like a bunch of different pieces. So when starting off with machine learning, I would definitely go with Python first. Python is makes machine learning much easier. C++ is a pain in the ass already, so trying to do pain in the ass machine learning with that is even worse. So Python makes it a lot easier. So I have a Python crash course for you guys. After that, I would get into data processing. So most of the time with these models and projects, you're going to be spending 80% of your time cleaning the information to feed into the model. So cleaning means like making sure that it's in the right form, making sure you have the right information, making sure it's being trained on the right stuff. There's like always a saying, you say garbage in, garbage out. So if you put in a bunch of crap, at the end, you're just going to get a bunch of crap. So data processing, there's two different libraries, or there's two prominent ones to get this cleaning and processing correct, Pandas and NumPy. So Pandas and NumPy are two Python libraries that are like super, super useful. So if I go into Python for data analysis, I've got one on NumPy, Pandas. SciPy is like scientific library for Python. And okay, say for instance, I want to go into Pandas. Inside of Pandas, there's like a bunch of just notebooks over here. This IP, Y, and B stands for IPython notebook, just if you wanted an extension. But over here, there's like a bunch of like Pandas exercises. So if you go in here, there's a bunch of exercises with the solutions. So let me show you we'll do the e-commerce purchasing solutions. So this is what a Jupyter notebook looks like. I did not make this, by the way. This is from a Udemy course that I got, so I can just disperse it to you guys because I paid for it. But you guys can totally take this. I'll show you where I got it here in a minute. So this is a cell right here. So unlike your normal IDE, you can write code and run it once, or you can run this again multiple times. So each piece is you can put like a new code in here. And as you can see, it's like .head shows the top 5 records, just so you know. And if you run it, it'll show it right here, which is kind of cool. Whereas in like normal Python or C++, you have to hit print. Jupyter Notebooks just print it out for you, which is kind of nice. Let me see here. So this is just the Pandas one. I would learn that. It's pretty interesting. And let's go back here. This is just I'll go to the Python one. So this is like Python exercises. So right here, there's like a whole course on Python exercises that you can try and do. So say for instance, it says what is 7 to the power of 4. So we're going to go 7 to the power of 4 and press Command Enter and it'll run the cell, or you can hit run right over here. Yeah. And yeah, that's the answer because it ran. You can even duplicate cells, which is kind of nice. So if you wanted to copy a piece of code, you just say copy and then paste and it'll put it right there for you, which is kind of awesome. And you can run this without messing anything else up. If you wanted to do 2 plus 3 and run it, 5, which is kind of awesome. So you can kind of just run through these and get used to it. I'll give the link in the link's like really long to this, so we'll probably post it in the email afterwards. But in this bootcamp, there's like a bunch of stuff for you guys to learn. It goes all the way through to data visualization, so making graphs and all that good stuff with Seaborn. And he has like machine learning sections. So he has all the different algorithms that you guys can learn about. So each one has got a solutions manual, just like a general notebook, and exercises you can go through. And I've even got one on deep learning over here. So like there's TensorFlow stuff if you really wanted to get advanced like that. But like I said, I would start off with Python, probably do Pandas, NumPy, and then maybe go into the machine learning and do the visualization and then machine learning pieces. So it's a lot of work, but it's right there for you guys if you wanted to learn it. And like Amy said earlier, there's a bunch of videos on what to do, where to find stuff if you get stuck. I'm going to show you a few other ones that I normally get as well. Like I think, yeah, this is my Udemy. I think they get most of their money from me because I just buy everything. So you can spend a lot of money on this site. Honestly, go for the sales. So they have like $10 sales and you get like $200 courses for $10. It's totally worth it because they don't teach any of this stuff at UCI unless you get into like machine learning classes and all that. But frameworks like web frameworks like Angular and React and all those good things, they don't teach them here unless you go to some workshop and it'll be here. So I bought like React 16. I have Docker stuff here. When I was learning Python, I have this guy, Dart and Flutter, which is like a cross-platform mobile. Udemy is awesome, but you can spend a lot of money. So like I said, go for the sales. That workshop I showed you is all Udemy stuff. It's kind of a really great resource that is like pretty cheap. Like
Is the machine learning one any good? I see you only got like
Oh.
2% done, but was it any good?
Yeah, I pick out all the videos I want to watch. I want to watch like 12 hours of videos. So if I have a problem, I normally just go and find it.
Is it good though? Is it
Yeah, these two are great. Machine Learning A through Z or whatever is pretty awesome. They're on Kickstarter. So these guys were sponsored on Kickstarter and then made this. Yeah, so that's like a really good course to get into. It's a little bit more intense because there's no like startup. They're kind of like, here's machine learning. So I would definitely do like some of the Python stuff, like I said, the data cleaning stuff, and then go into that because they just go straight into it. But yeah, Udemy is a great place to go. Like they even have stuff on Google Cloud. And here's a whole complete guide to TensorFlow if you wanted to do that. But yeah, back to this. So like I said, Jupyter Notebooks are awesome for super simple stuff. But as soon as stuff gets like way more intense and you're using way more memory and it's taking a long time to run, I would definitely use Google Collab. So this is like pretty much a like a Jupyter Notebook, just it's run on Google servers. So I'll show you how to set this up. You have access to a GPU and a TPU. So GPU is a graphics processing unit. TPU is a tensor processing unit. So specifically for machine learning. They give you 12 gigs of RAM, which is pretty awesome. And saving and uploading files is pretty simple. I'm going to show you how to set one up, and I think you just have to log in and you're good. So if you go, it's called Collab at research.google.com. You can pretty much just Google Collab, and it'll come up. I'll go to this link. So it just looks like this. You can get files from your Google Drive. You can upload them or go through your GitHub. It's pretty awesome. Or you can just say new Python 3 notebook. It'll take you to something that looks exactly like when it loads. Now it'll look exactly like a Jupyter notebook. So this is running on a CPU on Google servers. This is not running on your computer, so it runs way faster. It's great for training stuff. And if you want it to run a little bit faster than that, you can just go edit. You can go notebook settings, and you can say, I want to run this on a GPU, which is pretty cool, or a TPU. You just click on that and hit save, and it'll pop up, which is pretty awesome. And you can run whatever you want on there and save it to your Google Drive. It's like super, super simple, especially like having to spend huge amounts of money on like a whole hardware kit to like get the stuff to run quickly. Costs like $3,000, $5,000, whatever. This is super cheap, free, and easy to set up. Like took like 3 seconds. But like I said, it does have limitations, 12 gigs of memory. Sometimes models get a lot bigger than that. And Google can throttle you, I'm sure, because you're on their servers. They can do whatever they want. So if you don't want to do that, I would get into, let's see, let me get my presentation back. I would get into Google Cloud. So this one is way more powerful. It takes a lot more to set up, but you can run models for weeks on this thing, which is kind of awesome. I've never had to do that. I think the longest one took me about 2 days. That was pretty crappy. But it took, and you guys get, when you log in with your UCNet ID, do the free trial, you get $300 to use this stuff. So Google Cloud comes with the platform itself, doesn't only have ML Engine. ML Engine's good for training models and storing models, but it's also great for like deploying applications. It's great for IoT stuff. If you wanted to do Google storage, anything like that, just using their servers, Google Cloud platform is awesome. So I will say that their documentation is not the best. Everything is there. You've just got to find it. And that can be frustrating. So if you guys want to log in and just go to Google Cloud Console, once it actually loads, you'll get this. You just create a project over here. This is one of my projects, or Ryan and I projects, and you get all this stuff that comes with it. So you get App Engine, Compute Engine, all this good stuff. The one that I would look at is ML Engine over here. So ML Engine, you submit a job, it would train for you, so you're not using your computer. But like I said, that's only for stuff that's way bigger. Stuff that'll break your computer and was not big enough for the Collab. ML Engine is awesome. But it takes a long time to set up. Okay, so let me get back to my presentation. Do you guys have any questions at all? Like I said, I'll post the link for the bootcamp up on the email, so you can just download it whenever. And Jupyter is, if you have any questions on Jupyter and how to set it up, it takes like 3 commands. I'll show you in a minute. All right. So yeah, like I said, we have the bootcamp, but we'll post that up. Do you guys have any questions for me at all? All good? All right. I'm gonna transfer to Monish, and yeah, sure.
So for the machine learning on Udemy, you said that to not do that right away if you are not experienced.
Yeah, like I said, you can start there, but they're gonna go over Python and do the cleaning by themselves. Like they're gonna go straight into that, and sometimes it can be kind of daunting if you haven't looked at Python before.
So if you know Python?
If you know Python well and you can kind of pick up on like the pandas and NumPy, then it's super great. But they'll just roll into teaching you machine learning methods and stuff. So I would totally do that, but you feel it's a little bit intense, just do a crash course. They take a few minutes, sometimes like a day or two, but there's exercises and all that good stuff, and there's tons of resources to go and learn Python and all that. But if you're going straight from zero to machine learning, it might be a bit scary. Yeah. Good question. All right, I'm going to head over to Manish, and he's going to teach us some stuff.
Okay.
Right. Hello, everyone. I'm Manish. I'm also one of the mentors. I don't know if you guys, if anyone's been here last year, I guys taught you guys TensorFlow. This year, I guess there's a lot more new faces, so it's a good sign for the club. So today I'll be talking about how to read research papers. A lot of people, when in kind of like my day-to-day life, have asked like, how do you just like learn or know so much about machine learning? And it's really through research papers. Classes will only take you to a certain amount. But if you want to get to like the next level, it's all about reading research papers, understanding how to read them, what information is necessary, what isn't, because there's a lot of information. Some of it's pertinent to you guys, some of it's not. And based on whatever skill set, what kind of job you want, it's kind of important to realize that what sections of the paper you guys should really look into. So that's what I'll be doing today. Oops, that's not. Come on. There we go. So we'll be looking at a research paper that I know pretty well. It's called Convolution LSTMs. Does anyone know what those are? What is a convolution neural network and what is an LSTM? No one? What? All right, 2 people. That's fine. That's good, because I don't want you guys to know what it is, right? Because that's the whole point of this. You already know what it is, and there's no fun in reading a research paper, right? But I mean, this paper is again on our PowerPoint presentation. It'll be posted, I guess, with the email that's be sent out. You guys can read this on your own. It's a very interesting paper. I'll tell you this. This is a very common paper. How do we? That one?
Mm-hmm.
Okay, cool. I don't have a Mac. I have a PC. So.
I'm sorry.
This is a very typical paper. This is about like 60% of the papers that you'll see. This is how they're formatted. About 20% of them will be much simpler than this. They'll have more pictures, so you can kind of look at it and like, hey, that's how it looks. Another 20% don't have pictures at all and just have math. And for those, I would say don't use those papers unless you're really into math. But this is a good representation of a majority of papers out there. And so that's why I picked this one. So starting off, everyone knows what an abstract is. Well, in machine learning, it's a little bit more important because reading it kind of tells you what exactly you're doing, right? What is this paper trying to accomplish and why is it doing so? And in this case, we're dealing with issues with text analysis, or what's known as sentiment or text classification, or sentiment analysis is another way to put it. It's kind of understanding when we have the bigger picture really is when we have a sentence, we want to understand what that sentence is trying to communicate. So in this case, if let's say I want to get food from McDonald's, that's a request, right? And that's what we want to tackle in this paper. So just reading a little bit about the abstract, right, will kind of get you to that point where what are they trying to use to solve this. And in this case, we're using a convolution neural network and a recurrent neural network. They're the two primary architectures being used in this paper. And so if you don't know what those are, you go read about those, right? What is an RNN? What is a CNN? And you guys will, through this course or the club meetings and our workshops, you guys will learn that an LSTM is a fancy RNN. So just putting that out there so you guys can kind of follow along when I say LSTM and RNN. All right. So kind of starting off with what an introduction kind of gives you the paper, it's describing what the problem is, right? And in this case, the issue is trying to represent sentences as meaningful features for task sentiment classification, right? Now, it's a lot of jumble, but basically it's what I said in the beginning, right? It's describing a sentence in kind of like one word. It's like summarizing a paragraph, basically, right? And that's what we're trying to accomplish with this. And so what are some of the issues with that? Why are we creating this neural network? Or this typical what's called architecture. When we say CNN LSTMs, these are architectures, and so we're trying to recreate a different architecture to help solve that problem. So what are we trying to do? And it's basically we're trying to capture local concurrent correlations and spatial and temporal structures. So how are they doing so? Well, if you read about CNNs, you'll know that a CNN is very good at spatial recognition, very good at spatially understanding what data is there, right? In a very spatial area. It's not very good at temporal stuff. RNNs love temporal stuff. That's all they're built for. LSTMs they're called long short-term memory. So by, just that phrase alone should say this is all about time, right? Having sequential data is important to them. So what happens if you combine them? It's kind of what this paper is, the gist of this paper is, right? What happens if you combine a spatial a neural network or a spatial architecture and a temporal architecture, right? What is the outcome? And so the introduction kind of gives you that, but if you're already familiar with the subject and you know exactly, the type of information that you're looking for, it's not something that's important to you guys, right? It's kind of like why are we doing this? What's the problem we're trying to solve? But if you've already recognized that you have a problem and you're trying to solve it, then you can skip this part, right? And it's important because introduction, this is relatively short. It goes on to 2 pages. That's short. I've seen them that are like 5-6 pages because they have a complex problem that they need to solve, and reading those is labor intensive, and oftentimes they use very large words that just do not coherently work to solve your problem. So yeah, and then typically you'll have another related work section. Related works typically discuss like what has this professor do, to solve the same problem? What has, these professors done to solve this exact same problem? And what are we doing differently compared to them, right? It's kind of your justification as to why your work is better than other people's work, right? It's your area to boast. And so that's why, reading about it may give you some leverage saying that, oh, there's another professor with a different architecture, right? And also, there's also, people who've done something similar. Let's go follow their work as well, right? So it's a gateway, basically. If you ever guys use Wikipedia, you guys have the references at the bottom. It's practically what this part is doing is acting as that reference link, so you can go and look at what other people have done. Right. So, what is the first thing you guys notice? Can someone tell me? It starts with a P, please.
The picture.
Yeah, thank you. You guys have noticed the picture, yes. If you're lucky, this is what you'll get a nice, pretty picture of what your model should look like. At first glance, to people who are not, who don't understand quite what a neural network is and what to look for, this picture means nothing. But to me, I've done this for like 2 years, so I know exactly what I'm looking for. And to me, I see this is the convolution part, and this is the LSTM part, right? When we describe these, we see the feature maps, we see windowed feature sequence. That's basically the output of your convolution layer. When we parse your convolution, you'll create a giant volumetric data tensor that you kind of just you need to understand, and so that's what that is, and so you're passing that to your LSTM. So I know exactly what to do when I'm building TensorFlow, PyTorch, when I'm writing the code, I know exactly what I'm looking for, right? And this comes with experience. It's really hard to read these diagrams sometimes because there's no set standard to how to read a diagram or how to write a diagram, because it's kind of just a free-for-all for everyone. You'll find that a lot. That's why the math papers are so difficult, is because some people use certain letters for a certain meaning, other people use it for another meaning, and so it's like very difficult to really discern what they mean when you say like, oh, what is theta? Some people consider theta the input, some people consider it a modification function of some kind, right? Some type of signal processing. So that's why, you know, it's difficult to really discern the math. So that is why I didn't choose the math papers, because we'll be here forever if we go through that. But yeah, luckily we have an image, so you know what the neural network looks like. As a programmer, that might be your last step, right? That's all you need to do, you're done. But let's say you have, you still want to implement your neural network, you need to implement the training functions, right? So that's where we need to go further. We have to delve further into the paper. And so typically, most papers are broken up into 5 to 6 sections. 1 and 2 are typically just introductions, discussing what the problem is and how to solve them. We have section 3, which is actually discussing the model, right? What is your model? What is implemented in the model? So in our case, they call it a CLSTM, and that's just convolution LSTM, right? And so describing that, you got some feature extractions. When we describe feature extractions, does anyone know what that is? Alrighty then. What that means is basically looking at a sentence and looking at patterns, right? And representing those patterns as tensors or vectors, right? Or arrays, depending on what your vocabulary is, right? If you want to think of it like if we have, most common way to think of it is what's called word vectors. It's representing a word as a 300 float point array or tensor, right? And so we do feature extraction. Nth-gram is just a process of creating these feature extraction maps to process further. And so that's basically your input. We have some pre-processing, and and then we talk about the model, what an LSTM actually is, long short-term memory networks, describing that. We have some math describing, can anyone discern what those are? It's just a bunch of activation layers, right? And so understanding that is not as critical if you're a programmer, because everything's been abstracted out in the coding side. If you're going into the mathematical field or the math aspect or the performance aspect, some people do like to program the back end for like TensorFlow, then understanding what's going on in the math is kind of important. So this paper may not be as useful to you as you might think, right? But if you're just being a programmer, I guess you can ignore it if you want, or you just read it. Section 4 is typically where we start delving into the results of how well your neural network has done. Also kind of the training process, and this is where most programmers will gain the most benefit because they'll know exactly what to do. So typically when we're building a training process, there's 3 steps. Pre-processing, where we see with the nth-gram feature extraction, the actual neural network building, and then the training step, right? So training is obviously a very difficult process, and so that's why a lot of papers describe how they train their network so they can replicate the results, right? Because everything we do is an experiment in machine learning, so it's important to have you're able to repeat results. I'm at a loss of words, sorry. But yeah, so again, padding and word vector initialization, discussing kind of parts of the model, what they are and how they work. Regularization, you guys will come to learn what that is as you continue through our workshops, but regularization is a very important factor. It introduces entropy into our neural networks. And does anyone know why entropy is important? Well, you can't have, basically that's how our brain works, right? Neural networks are designed to replicate our brain, and our brain is not ordered, is it? It's not as like ones or zeros, it's like one in between of zeros, right? And so like we want to introduce as much noise and entropic features as possible while still maintaining some sort of order. You want an input and you want to get a specific output. And so regularization helps to improve that by introducing some entropy, not too much. Too much will obviously cause your network to degrade, but yeah. So getting into the experiment, this is typically where a programmer wants to pay the most attention. A mathematician can kind of sleep on this one, just because it's not too important. Unless you're a statistician, then it's very important. And so we talk about, use of GPUs, hyperparameters. You guys will come to learn that hyperparameter tuning is probably 90% of the work of training a neural network. You have, a huge chunk in trying to trim the data and clean up the data. Then you also have a huge chunk of time dedicated to training the network. And so tuning hyperparameters, like how many features do you have in your neural net or your convolution layers? How many dense networks or dense layers do you have in your RNNs? How many layers are your RNNs consistent of, right? So it's like it's numbers that impact the overall model, right? How many convolution layers, right? We have many different models. How do you decide on which one it is? So that's what hyperparameter tuning kind of is. It's your adjustment. So they describe a lot about it. Of course, experiments. How well did their results come out to other people's results, right? And so their implementation typically they're hours. Mine, as you can see, they've done some pretty well. They've hit like 87, 86%, which is not the best, but for the process that it's doing, may be good, right? Again, it's all subjective. People may look at this differently. So you may not choose this paper. You may choose the one on CNNs with multi-channel. Up to you, right? So yeah, here, we're talking about actual networks. So they got a filter length of 3. When you're dealing with convolutions, you have kernels, which are basically the filters that you pass over your image or pass over the data. And so they're using single dimension convolution. And so they have a filter, or like they're looking at 3 words at a time. In this case, it's 300 length arrays at a time because they have vectorized their data. They don't actually look at characters, they look at vectors. Yeah, and then we have LSTM, some stuff about the LSTM where we talk about the number of kind of dense nets inside, or the size of the dense nets inside the LSTM, which is 300. So yeah, and then we talk about learning weights, because again, this is an experiment. Everything we do in machine learning is an experiment. It's never been done before, therefore you need to replicate the results. So they describe this in heavy detail, what exactly they did. Most papers, it's like a 50-50 shot whether or not you'll get the exact data about what they did. Sometimes they'll say like, oh, what system they're using, what GPU, how much memory it took up, how many epochs is another important feature. That's described. Where is it? It'll be described soon, I believe. But yeah, it's having a concrete understanding of what to do to replicate the exact same result is incredibly important. Typically, they also describe the data. Most data that you'll come across has its own papers, and those need to be read separately, right? Because you need to understand what the data you're looking at, because there are data scientists who have gone in and cleaned up the data, removed erroneous data, who've introduced better approaching data. Certain neural networks will approach data a certain way, right? So we'll have papers on top of papers describing what exactly the data set that we're using. For example, MNIST has about 200 papers or something on it, right? And MNIST is just handwritten numbers, right? So there's a lot of information. Yeah, this is all fun stuff. Ooh, configurations. Yes, this is all remember we talked about hyperparameters. This is basically where they describe which hyperparameter selection did the best, right? And it looks like S3 did the best. And so we start looking at what does S mean. S means a single convolution layer. So assuming they have 3 convolutions. And of course with the same filter length, so I'm assuming filter length of 3. A lot of assumptions there, but again, if you delve deeper into the paper, you may have a better understanding of exactly what's going on. And then, conclusion, getting down to conclusions, what exactly they've discovered about their convolution LSTM, why theirs is the best, because and how they can improve it, right? They describe exactly using a 3-gram feature extraction. And that goes back to nth gram feature extraction. That's an algorithm used to basically extract information from a set of words. Describe those in a vector. And so, yep, and that's basically it. We describe, again, all the sources they've used, because in a research paper it's incredibly important to cite your citations, because plagiarism, right? And that too, it's important to just cite people, because if someone wants to question your credibility, then you can just say, haha, I have proof, I got receipts. So yeah, if anyone has questions about how to read a paper. Yes.
Where do you find these research papers?
Where do I find these research papers? Yes, I find them on Google Scholar. You can find them on the UCI's internal network. I forget what it's called. You can. I mainly use Google Scholar just because a lot of them are published by Columbia, and you can just find them on. There's Google Scholar is a good one. It's again looking for what you want to look for, right? When I searched this, I was looking for text classification using LSTMs, and I found something on CNN LSTMs, right? So that's something that it's basically you want to keyword your search for exactly the network that you're planning on using. I had a question in the back. Yeah.
What type of math is usually used in these types of papers?
What type of math? I mean, it's like linear algebra. Most of the math is, again, they'll have sigma as to describe you're basically doing all your calculations on a matrix. So rather than writing out your matrix equation, they'll have they'll describe it as some type of sigma function or some type of summation. Understanding the summation isn't the important part. Understanding what the symbols are, understanding when you're dealing with, for example, we'll talk about what activation functions are, right, and how we use activation functions, how important they are in a neuron situation, a neural net situation, right? So if one researcher describes activation function as sigmoid, right, then having that understanding that they're applying sigmoid to a matrix is important, right? So the math is really, it's an abstracted linear algebra, right? Where you're not actually, they don't physically describe it as being done on a matrix, but mathematically they showcase it by just having a summation. Thank you everyone for coming out. Yeah.